Question number 1.227. An artificial satellite of Moon revolves in a circular orbital whose radius exceeds the radius of Moon by eta times. Okay, so this is Moon and an artificial satellite is moving in this orbital. Let's suppose its mass is small m, mass of Moon is capital M. If radius of Moon is r, then radius of this orbital is eta into r. This information is given. Okay. Now, in the process of motion, satellite experiences a slight resistance due to cosmic dust. Okay, it means there is a resistive force which is dependent on the velocity, and this force F is given as alpha into v square. Okay, where alpha is a constant. So we have to find out how long the satellite will stay in the orbit until it falls on the Moon. Okay, so because there is a force which is opposing the motion, so it will constantly reduce the energy of this object, and as the energy starts reducing, the orbital radius will start reducing for this satellite, and after certain time it will collapse on the Moon. Okay, so we have to calculate its time required for this. Okay, so we can apply first of all simple fundamental of Newton's law, that change in momentum, rate of change in momentum is equals to applied force. Okay, so for this satellite, this is mass is constant, so we can write m dv over dt is equals to F, that is alpha v square. So we can rearrange this expression that dv over v square is equals to alpha over m into dt. Okay. So we are writing this equation as 1. Will perform further operation after determining some condition. Look, initial condition is radius of this satellite is n into r. Okay, so if this satellite is moving with velocity v at this point, okay, so we can write that mv square upon r, condition for circular motion, is equals to gravitational pull gm, mass of the object, into mass of Moon upon r square. Right now it is eta r. Okay, so mv square upon eta r is equals to eta r square for this particular time. Okay, or for any general time we can also calculate. So it's not a big deal. Let's see. The velocity of this object, okay, at this point when it is rotating in this orbital, will be m, and m is cancelled out, so it is under root g capital M over eta into r. Okay, so we can consider this velocity as initial velocity. Now when it reaches just near to the surface of Moon, then again we can use this expression, but in this case we'll replace this radius by r, only radius of Moon. Okay, so this is mv square upon r is equals to gmm over r square. Okay, when this satellite will collapse on Moon. Okay, so v is equals to under root gm over r. Okay, this is final velocity. So this particular question comprises of very different approach. Okay, where we are determining the time when the satellite will collapse on Moon by using the change in velocity of this object. Okay, so initial velocity is this, final velocity is this. Now we can integrate this expression. Okay, let's integrate. So if we'll integrate, so initially time t equals to 0. Suppose it collapses after time t. So when we started observing this satellite, then its initial velocity, let's take vi, which is given here, and when it will reach collide with Moon, then velocity is vf. Let's solve this expression. So in this case, dv over v square and integration of v square is minus 1 over v. Okay, So we can write this is 1 Vi minus Vf. Okay, because it is minus 1 over V and limit is V and Vf, so we can solve simply this expression, and this is alpha over m and differentiation is t. So we can put this Vi and Vm here. So we are getting t equals to m over alpha. This is 1 over under root gm over eta into r minus 1 over under root gm over r. Okay. Now if we'll recall the relation for gravitational acceleration, that is gm over r square, then we can replace gm over r by g into r. Okay, just for the sake of simplification of this expression. So we can take out this term under root gm over r from this entire expression. So we can write here t equals to m over alpha under root gm over r from there, and if you take this term, then we can write under root eta minus 1. This is gm over r can be replaced by root gr. So t is equals to m over alpha root g and multiplied by root eta minus r. This is our final answer, that when this satellite will collapse on moon.